Let's begin / continue our journey talking about solving systems of linear differential equations. Today is February 7th. That's 7, sure. All right, so solving systems of linear differential equations. All right, so here's the setup. And we started this last time, but we didn't really find the solution. We just talked about kind of what it represented. So we're going to try to solve the following system, where the derivative of x1 with respect to t is equal to negative x1 plus 2x2. The derivative of x2 with respect to t is equal to negative 3x1 plus 4x2. And we're also given that the initial conditions are that x1 at time 0 is equal to 2, x2 at time 0 is equal to 4. I'll remind everybody that x1 and x2 are both functions. They are functions of time, and we're going to find them. Here's the process, and it's a bit of a lengthy process. So in words, the process is find the eigenvalues of the matrix, or I should say, first write it as a matrix equation. So here's what we're going to do. We're going to, 1, write it as a matrix equation. 2, find the eigenvalues of the matrix, which we typically use the Greek letter lambda for. 3, find the eigenvectors. 4, write the solution, which is going to be, that our vector x consisting of x1 and x2 is going to equal c1e to the lambda 1t times v1 plus c2e to the lambda 2t times v2. And then finally, solve for our constants c1 and c2 using the initial conditions. So there's kind of a lot to do here. It is pretty rote, though, meaning like it's always the same 5 steps. It's always find the eigenvalues, find the eigenvectors, et cetera, et cetera, et cetera. So let's start off by writing this system of differential equations as a matrix equation. So we're just going to write this as the vector dx1 dt dx2 dt equal to the coefficient matrix, which is going to be -1, 2, -3, 4, multiplied by the variable vector x1, x2. I had notes somewhere. Sure. I don't really need them at this moment, but just make sure that they're available to me. Sure. Cool. All right. I'll point out that people often write this as the derivative of the vector x equal to the matrix A times the vector x. So x is that, A is that, and the derivative of x is that. Just because you'll probably see that notation at some point. All right, so first things first, we're going to find the eigenvalues of our matrix. So in general, to find the eigenvalues, we're going to solve the determinant of our matrix minus lambda times the 2 by 2 identity matrix equal to 0. What this ends up being is a quadratic equation. And I'll show you all the work, but I'll tell you the easy thing you should do. So here's the actual work. We're going to take the determinant of our matrix, which is -1, 2, -3, 4, minus lambda, which is just a constant, like it's like an A or a B or a C or whatever that we're trying to solve for, times the 2 by 2 identity matrix, which is just the matrix 1, 0, 0, 1. You don't really need to know that larger matrices also have identities, but like there's a 3 by 3 identity, which is just 1s on the main diagonal and 0s everywhere else, and so on and so on. But I will point out that, what was I going to point out? I don't know. Oh, I was going to point out that we call this matrix the identity matrix because when you multiply by it, you don't change anything, right? It's like multiplying by the number 1. 5 times 1 is still 5. A matrix times this identity matrix will still be the exact same matrix you started off with. So then what you should do is not write this down. I mean, you should write this down now, but like when you're doing this, you shouldn't write all this down. You should just say, hey, I'm going to take the determinant of, actually, I'm going to write down one more step that you shouldn't write down, of my matrix -1, 2, -3, 4, minus, I'm going to distribute the lambda and get lambda, 0, 0, lambda. And then what you should actually write down is none of this. You should write down the determinant of -1 minus lambda, 2 minus 0, -3 minus 0, and 4 minus lambda. Or in other words, when you're starting off this process of finding the eigenvalues, you start by writing the determinant of your matrix where you're subtracting lambda from each of the diagonal spots. And again, when I say the diagonal, I mean the thing that starts in the upper left corner and ends in the lower right corner. Or alternatively, all the entries where the row number and the column number are the same, right? In this first spot, the row is the first row, first column, for second row, second column. Who remembers how to take the determinant of a matrix? Of a 2x2 matrix, I should say. It's not too terrible. I'll remind you over here, though. So that's what I'm going to give here. So the determinant of a 2x2 matrix, A, B, C, D, is the product of A and D, or as I would say, the product of the diagonals minus the product of the off diagonals. So AD minus BC. Here, that's going to be -1 minus lambda times 4 minus lambda, minus 2 times -3. We're going to set that equal to 0 and solve. A lot of the time, and so this will always be a quadratic equation because you're always going to get a lambda squared. And a lot of the time, you will be able to solve this by just factoring, but some of the time, actually more than some of the time, it's not going to factor, and you are going to have to use the quadratic equation because I'm going to tell you right now, sometimes your eigenvalues are going to be imaginary. We're going to have square roots and negative numbers. It's something we have to cover that isn't something we can avoid. So yeah, a whole class of solutions depends on the eigenvalue being complex, aka imaginary. So solving this one though, we're going to get negative lambda times negative lambda is positive lambda squared. I have a -4 lambda plus lambda, which is a -3 lambda. And then I have a -4 plus 6, that's going to be a +2 equal to 0. This does factor. It factors as lambda -1 times lambda -2 equal to 0. So we get two eigenvalues, lambda equal to 1, lambda equal to 2. We typically give the eigenvalues subscript names, so like to distinguish them. So we call them one of them lambda 1, one of them lambda 2. And usually you would call the bigger one lambda 1 and the smaller one lambda 2. It doesn't actually really matter. Here, to be not confusing, I'm going to call 1 lambda 1 and 2 lambda 2 because it feels like it'd be confusing to do it the other way. You say that's lambda 1, that's lambda 2. But again, it doesn't really matter what you name them. The reason we name them is so that we can keep the eigenvalue, eigenvectors paired together appropriately, right? Because each eigenvalue goes with a certain specific eigenvector. Cool, so we found the eigenvalues. Now we're going to find the eigenvectors. There's a couple ways to find the eigenvectors. And I'll show you both because I think they're both worthwhile. So let's start with lambda 2 equal to 2 first. So lambda 2 equal to 2. So what an eigenvalue and eigenvector are is the thing that if you multiply the matrix by the eigenvector, you end up getting just a multiple of that eigenvector. That's why it's special. So what's going to happen is we're going to multiply this matrix by this vector, and it's not going to change the direction of the vector, but it might change the magnitude. So here's what we're looking for in this case. We want to say, okay, great. We want A times our unknown eigenvector to equal the eigenvalue times our unknown eigenvector. That's the whole point. So in this case, what that's going to mean is we're going to have that the matrix A, which is -1, 2, -3, 4, times the vector we're looking for, which I usually like to call, I like to call it xy usually, but it might make more sense to call it x1, x2 here. No, I still want to call it x. Let me see what I did. Let me look at what I did in my notes so I can be consistent here. Bless you. I used x1, x2. All right, fine. That's going to equal 2 times x1, x2. Most of the time, nearly all of the time, you only need one of these equations. And what do I mean by one of these equations? Well, this matrix equation here is really a system of two equations. It's -1 times x1 plus 2 times x2 equal to 2 times x1. And it's -3 times x1 plus 4 times x2 equals 2 times x2. And most of the time, both these equations give us the same relationship between, well, I should say, if they both don't work, it's because one of them doesn't give you any information. Like sometimes you'll get an equation that'll be like x2 equals x2. Right? Well, yeah, that's true, but it doesn't help me say anything. So if we look at both of these, if I isolate x2 over here, I'm going to add x1 to both sides. So I'm going to have 2x2 equal to 3x1. Or over here, if I subtract 4x2 from both sides, I'm going to have -3x1 equals -2x2. Those are essentially the same equations. So it's the same relationship between x1 and x2, regardless of which equation you use. The point being that you almost only ever have to look at the first equation. So you don't need to write both of these out. I would never write both of them out. I would only write both of them out if the first one didn't give me anything, which we'll see an example of a little bit later on. So cool. What this tells me is that, and I would say you don't want to go any further than this. You could divide both sides by 2 and say that x2 is equal to 3/2 times x1. That is not the easiest thing to do here. The easiest thing to do is to say, cool, I'm looking for almost any solution to this equation. There's one solution I don't want, where x1 is 0 and x2 is 0. Because 0, 0 never gets to be an eigenvector. It's kind of like the case where we're not interested in. But any other solution to this equation will give us an eigenvector. So the easiest solution in my mind to find is let x2 equal that coefficient and x1 equal that coefficient. So we're going to say, great, x1 equals 2, x2 equals 3. So my eigenvector is going to be the vector where x1 equals 2 and x2 equals 3. Are there other options? Yes, there are. Literally any multiple of this eigenvector except for 0, 0 is also an eigenvector. I don't feel like I have anything more to say about that one, really. You can do other things though, right? If you really, really wanted to, you could have isolated and said x2 equals 3/2 x1, and you could have picked x1 equal to 2 and gotten x2 equal to 3, or you could have picked x1 equal to 1 and gotten x2 equal to 3/2, or pick any other number you like that isn't 0 and see what you get. So I'll just point out, right, this also would have been perfectly fine, like -10, -15 is also an eigenvector for the eigenvalue of 2. The standard or typical choice, if it's available, is to pick the vector with integer values that are as small as possible. So this would be the standard choice here, 2, 3. Which is what your teacher would typically choose. All right. Also, in case any of you on Zoom have questions, feel free to chime in either in the chat or by unmuting yourself. I'll probably see it at some point. Let's find the other eigenvector. So for lambda 1 equal to 1, and actually, so I'm going to find this one a slightly different way. So I prefer doing it this way. I think I like this way better because it kind of retains the meaning of the eigenvector. That the whole point is that the matrix times the vector equals a multiple of the vector. In fact, before we move on to the second part, I'm going to over here real quick. I just want to point out that it is true, right? If you take this matrix, note that your matrix A, -1, 2, -3, 4, multiplied by the vector we just found, 2, 3. If you multiply it out, you're going to get -1 times 2 plus 2 times 3, right? First row, first column. And then -3 times 2 plus 4 times 3. second row, first column. And that's going to end up being, let's see, -2 plus 6 is 4, -6 plus 12 is 6. And that is, not surprisingly, exactly 2 times the vector that we started with. So that's the whole point of the eigenvector, is that when you multiply the matrix by it, you just end up getting a multiple of it. And the multiple is always whatever the eigenvalue was. It would have also worked, and you should check for yourself, it would also work if our vector is -10, -15. If you multiply your matrix by that vector, you should get -20, -30. You should check on your own. Okay, back to up here though. So if I look at λ1 equal to 1, instead of doing it this way, the alternative way is to say we're going to solve a minus lambda I multiplied by our eigenvector equal to the 0 vector. Essentially, you're subtracting this over to the other side, and then you're kind of factoring out the vector. But to factor out the vector, you have to have the right kind of size thing over here. So that's why you need the I there instead of just λ1. Let's take a look and see. So in this case, my a minus lambda I is going to be a, which is -1, 2, -3, 4, minus 1 times the identity matrix, which what I really should have done is just subtracted 1 from each of the diagonal spots. So that's going to be the matrix -2, 2, -3, 3. And then that matrix multiplied by the eigenvector that I don't know yet should end up equaling the 0 vector. So let's see. I think the one thing I do like about this is that it's more obvious that both equations are the same equation, essentially, right? Whether it's -2x1 plus 2x2 equal to 0, or the other equation, -3x1 plus 3x2 equal to 0, we can kind of see that those are just multiples of each other. So solving this one, I get 2x2 equal to 2x1. Since both of them can be divided by 2, I'm going to write this as x2 equal to x1. So here the eigenvector, I'm going to pick 1 for x1 and 1 for x2. V1 is going to be the vector 1, 1. Personally, this is not my favorite, but if your eigenvalues are not nice, meaning they're not integers, you had to use the quadratic formula and you got something that was like 1 plus the square root of 3 divided by 2. I should say 1 plus or minus the square root of 3 divided by 2. Then doing it this way is usually computationally easier. So we'll come back to that when we have less nice examples later on. I'm keeping track of where I'm putting things. Okay, sure. All right, we've got our eigenvalues, we've got our eigenvectors. Now we need to find the solution. The solution is actually the easy part, I think. So for the general solution, right? Because just like when you're solving a differential equation, there's the general solution that's going to have some constants in it, and then the particular solution where we solve for those constants. So here's our general solution. I always like to write out the formula just because it helps me remember what's going on. So my general solution is that the vector x, which is really just the components x1 of t and x2 of t, is equal to c1e to the λ1t times v1 plus c2e to the λ2t times v2. And now we're going to write it out. So we're going to say that x1 of t, x2 of t is equal to, we don't know what c1 and c2 are yet. So c1e to the λ1 was 1. I don't really need to write 1 times t, I'm just going to write t. Times v1, which is the vector 1, 1, plus c2e to the 2 times t times v2, which was 2, 3. Obviously, you should ask questions if you have them. I don't feel like I feel like I need to say that, but obviously I do feel like I need to say it because I say it all the damn time. But you should ask questions if you have them. So now we're going to go ahead and find the particular solution. Actually, let me look at my notes real quick here. 1 second. Yeah. Cool. Yeah, let's find the initial conditions. So or let's find the constant. So our initial conditions were that x1 of 0 was equal to 2 and x2 of 0 was equal to 4. Most of the time for problems like this, your initial conditions, they don't have to be, but it's very inconvenient if they're giving you a value other than 0 to plug in. Almost all the time it's going to be whatever the first one at 0 is, whatever the second one at 0 is. Because if it's not 0, then this e to the t part doesn't go away, which is just kind of gnarly. So we're going to say, great. On the left-hand side, if I plug in 0, I'm going to get 2, 4, and it's going to equal c1 e to the 0 times 1, 1, plus c2 e to the 0 times 2, 3. Or writing this a little bit more nicely, 2, 4 is equal to c1 times 1, 1, plus c2 times 2, 3. There are a number of ways to solve this. I'll talk about 2 of them. So the way that probably might seem the most straightforward is just to write out the 2 equations. One equation is 2 equal to 1 times c1 plus 2 times c2. And the second equation is 4 equal to 1 times c1 plus 3 times c2. Right, just looking at each row kind of separately. And then I see that if you subtract the second equation from the first equation, the c1s will cancel. So if we subtract that, 2 minus 4 is -2. C1 minus C1 is 0 C1. And 2C2 minus 3C2 is -C2. So it looks like C2 is equal to 2. And then you can plug back in C2 into either equation. Let's plug it back into this one. Say, great. Then 2 is going to equal C1 plus 2 times our value for C2 is 2. Subtract 4 from both sides, and you get -2 is equal to C1. And that's fine as long as the numbers are relatively nice. Another way to do this, though, which your teacher probably will talk about, is to write this as a matrix equation. So you could write this as 2, 4 is equal to the coefficient matrix 1, 2, 1, 3 multiplied by the vector C1, C2. Question? So I took my 2 equations, right? That 2 was equal to C1 times 1 plus C2 times 2. And that 4 was equal to C1 times 1 plus C2 times 3. And then I said, yeah, since the C1 coefficients are the same, I know that if I subtract this equation from that equation, the C1s will cancel out and add up to 0. So I said 2 minus 4, -2. C1 minus C1, 0. And 2C2 minus 3C2 is -C2. Or you could solve it this way. So I've got this equation, and I know it's been a minute since you've done this, but the way you can solve a matrix times a vector equals another vector is, well, you can't divide by a matrix. Because sometimes the matrix is like 0, which is a problem. But you can, if it exists, multiply by its inverse. So just like you can solve 5x equal to 7 by multiplying both sides by 1/5, the inverse of 5, we can solve this by multiplying both sides by the inverse of that matrix. And there's a way to find the inverse. It's probably been a while since you found the inverse of a matrix, but I'll remind you that if your matrix is a 2 by 2 matrix, A, B, C, D, then the inverse matrix is equal to 1 divided by the determinant, AD minus BC, multiplied by, here's how you find the inverse. You switch the diagonal elements. So A and Z trade places. Make my D look like a D. And then the off-diagonal elements change signs. The point of multiplying by an inverse matrix is that when you multiply by an inverse matrix, you're essentially left with a 1. Really, you're left with the identity. But let's actually show the work here. So here I'm going to multiply both sides by the inverse. So let's see, the determinant of this matrix is 3 minus 2, which is 1. That's convenient. So I'm going to multiply both sides by the following. I'm going to multiply both sides by, I'm going to switch A and D, so it's going to be 3 and 1 instead of 1 and 3. And then the 2 and the 1 are going to be opposite signs, so it's -2, -1. Multiply by 2, 4, equal to, I'm going to do it on this side too. 3, -2, -1, 1, times 1, 2, 1, 3, times C1 and C2, which is what I'm trying to solve for. So again, I'll point out that in this example, we probably don't need to do this because the numbers are relatively not terrible, but sometimes the numbers are bad enough that you want to do it this way because it just will always work out. So let's see, on the left-hand side, let's see what I get. 3 times 2 plus -2 times 4 is 6 minus 8, which is -2. And -1 times 2 plus 1 times 4 is -2 plus 4, which is +2. On the right-hand side, I shouldn't have even written this really. On the right-hand side, I really should have just written the vector C1, C2. But I want to show you what's happening. So if you multiply this together, look what's happening here. You get 3. So I'll remind you, in case you forgot about matrix multiplication, it's rows of the first matrix dotted with columns of the second matrix. So first row dotted with first column, 3 times 1 plus -2 times 1 is 1. First row, second column, 3 times 2 plus -2 times 3 is 6 minus 6, which is 0. Second row, first column, -1 times 1 plus 1 times 1 is -1 plus 1, which is 0. And finally, second row, second column, -1 times 2 plus 1 times 3 is -2 plus 3, which is 1. Which should not be a surprise at all, because when you multiply inverses together, you end up getting 1. Or in matrices, you end up getting the identity matrix. And then if you multiply this out, 1 times C1 plus 0 times C2 is C1. 0 times C1 plus 1 times C2 is C2. And just like I said before, when you multiply the identity matrix by any other matrix or vector, you always just get back that matrix or vector because you're multiplying by 1. So look, we got the same result. C1 is equal to -2, C2 is equal to +2. So here's our particular solution to this to the system of differential equations. So let's write it. I'm gonna write it all down here. Come on, pages, stay where you need to be. So the solution to the system, I'll write it again here. It was dx1 dt equal to, I kind of forgot what it was, and I go back and look, equal to -x1 plus 2x2, and dx2 dt equal to -3x1 plus 4x2, with the initial condition that x1 of 0 is equal to 2 and x2 of 0 is equal to 4, is going to be this solution up here with the C1 and C2 values plugged in. C1 was -2 and C2 is +2. So the solution to the system is x1 of t, x2 of t equal to -2 e to the t times 1, 1 plus 2 e to the 2t times 2, 3. And although that's how I prefer to write the solution, it is maybe disguising the fact that we really have two equations here, or two solutions. There's the x1 and the x2. So let's actually write them both out. Even though this is how I would like to write it, let's be more specific here. So the way you want to read this is just by rows, right? The top row is all one thing, the bottom row is all one thing. So the top row here is that x1 of t is equal to -2 e to the t times 1 plus 2 e to the 2t times 2. Or more simply, -2 e to the t plus 4 e to the 2t. Similarly, x2 of t is going to be -2 e to the t times 1 plus 2 e to the 2t times 3. Or more simply, -2 e to the t plus 6 e to the 2t. kind of a lot. But not unmanageable. It's just there's a lot of steps to go through. Let's see. Question? Good question. What does this tell us? So it tells us that, well, it tells us that this is a solution to this system of differential equations. So what we found here, again, if we're thinking back to where x1 was representing a predator population and x2 is representing a prey population, that they are growing according to this solution here. So as time goes on, well, actually, what's going to happen as time goes on? Well, here's what matters the most. What matters the most is the largest positive eigenvalue. That's going to kind of tell you whether this population is growing or not. So here, if we look at x1 of t, which is equal to -2 e to the t plus 4 e to the 2t, we can see that the e to the 2t term is going to overpower the -2 e to the t term, and that this population is going to get larger and larger and larger as time goes on and on and on. If it helps, you could factor out an e to the t, right? You could think of writing this as e to the t times -2 plus 4 e to the t. And then it's a little more obvious that, oh yeah, t is going to infinity, that's going to infinity, and that's going to infinity as well. So certainly the whole thing's going to go to infinity. And in a similar way, x2 does the same thing. x2, which is -2 e to the t plus 6 e to the 2t, also grows and grows and grows as time goes on and on. That's not always going to be true. In other examples, we might have a case where both eigenvalues are negative. And so you're going to have like e to the -t or e to the -2t. And then as time goes on and on and on, things will get closer and closer to 0. C is just the constant. So it's not really telling us anything other than how to find the particular solution. So right, this is our particular solution right here, with the actual values of C plugged in. For our initial conditions, x1 of 0 equal to 2, x2 of 0 equal to 4. See, is there anything else I want to say here? I think we're good. Let's go ahead and look at one other thing. All right. So I want to remind you about kind of where this solution came from, at least ideologically. So writing the system again. So this quote unquote linear system of differential equations can be written in the matrix form. We already did that, but I'm gonna do it again. So the longer way of writing it is dx dt, and write that arrow to indicate that it's a vector, which was just the derivative of x1 is the first component, the derivative of x2 is the second component, is equal to -1, 2, -3, 4 times x1, x2. But really, the shorter way of writing this is just saying, oh yeah, the derivative of x is equal to a times x. And then I'll remind you that the idea behind the solution that we found is that from before, if the derivative of like regular x, not just a vector x, is equal to some constant times x, if that has the solution where x of t is equal to c e to the constant a times t, right? That's just from back from 17b when we talked about solving differential equations and how this system where the rate of change is proportional to the population size ends up giving us exponential growth, then it's not too far-fetched to say that the derivative of the vector x equal to some constant in quotes here times x has a solution like x of t equal to c e to the a capital A times t. But the problem is we can't really do that. So instead of using the matrix A, what we instead use is the eigenvalues and the eigenvectors of A to kind of stand in. So instead of x equal to c e to the at, I'll recall that the matrix A times the vector V is equal to lambda times the vector V. We can essentially say that x of t is going to equal what we already know is c1e to the lambda 1t times v1 plus c2e to the lambda 2t times v2. It's similar, right? We're using the lambdas instead of the a's, and then we have to throw in the eigenvectors to make sure we actually get vectors back. But it's very, very same in the idea of what's happening here. So, gosh, I forget how much time it takes to go through all this. I do want to show you at least one time right now that we actually did get a solution to the thing we said we got a solution to, right? Like I said it's a solution, you probably believe me. Well, let's actually show it. Now, you should never actually have to do this because as long as you follow the procedure correctly, the thing you get will be a solution. But let's actually go back and check. So is it true, or we're going to check that, let me go back to my notes here so I can see what they're written down. We're going to check that x1 of t equal to negative 2 e to the t plus 4 e to the 2t, and x2 of t equal to negative 2 e to the t plus 6 e to the 2t is in fact a solution to the system of differential equations dx1 dt equal to negative x1 plus 2x2, and dx2 dt is equal to negative 3x1 plus 4x2. I will point out, we actually could do this just using C1 and C2 right? We don't have to actually use the particular constants we found, but I feel like it's a little easier to use them to see what's happening here. So let's look at the first equation first. And all we're really going to do is we're just going to calculate both sides of this equation. So first we're going to find dx1 dt. So dx1 dt, well, I'm just taking the derivative of x1. So that's the derivative of negative 2 e to the t plus 4 e to the 2t, which is going to give me negative 2 e to the t plus 4 e to the 2t times 2, which is 8 e to the 2t. Cool, let's check the other side of the equation. Negative x, let's see some bullets here. Negative x1 plus 2x2, I'm just going to replace x1 with all of that and x2 with all of that. That's going to be negative 2 e to the t plus 4 e to the 2t plus 2 times x2, which is negative 2 e to the t plus 6 e to the 2t. Let's simplify that. That's going to be 2 e to the t minus 4 e to the 2t minus 4 e to the t plus 12 e to the 2t. And simplifying, 2 e to the t minus 4 e to the t is negative 2 e to the t. And negative 4 e to the 2t plus 12 e to the 2t is 8 e to the 2t. Hey, look, those are the same. And similarly, like if we were asked to check, we would still have to do the rest of this. We can also see that dx2 dt is just the derivative of x2, which is negative 2 e to the t plus 6 e to the 2t. It's a little tedious to do this, but it does work. You're going to get negative 2 e to the t plus 12 e to the 2t and negative 3x1 plus 4x2 is running out of room here. Negative 3 times negative 2 e to the t plus 4 e to the 2t plus 4 times negative 2 e to the t plus 6 e to the 2t. Finally, we get 6 e to the t minus 12 e to the 2t minus 8 e to the t plus 24 e to the 2t. And simplifying, 6 minus 8 is negative 2 e to the t, and negative 12 plus 24 is 12 e to the 2t. And again, we see that they are in fact the same. So that actually shows that the x1 and x2 that we found are actually solutions to this system of differential equations. Cool. You never have to do that unless you're asked to do it. Right? You probably never have to do that. Okay, so yeah, we probably shouldn't start another example because it's super long. So let's see a few more things about this. Where did you come from? Okay. So the thing is, there's a couple graphs that we talk about that go along with this. So if I was going to graph this, let's see how good a job I can do here. You know what? Why am I going to try and graph it by hand? Let me just show you what the graph looks like. So I want to point out a few things, though, which are kind of neat. Where are my graphs here? Cool. Yeah, go away. Oh, sorry, things are getting in my way over here. All right, so yeah, okay, Desmos, take your time. So I wonder if I can call it x1. Let's see what happens if I do this. x1 of t. Oh, I don't want that down there. Not that you really have to call it the thing. It just, oh, what, caps lock. Let's say that's equal to negative 2 e to the t. Cool, yeah, it works. Plus 4 e to the 2t. And yeah, not surprisingly, it gets larger and larger and larger as you go from left to right. Kind of like ridiculously big, right? Which exponential functions, right? They just get really, really big. Let's look at the other one as well, which was x2 of t equal to negative 3x1 plus, sorry, negative 2 e to the t plus 6 e to the 2t, which should get bigger even faster. I'm sorry, I forgot an equal sign there. That's kind of important. There we go. And you kind of can't, I mean, there's not a lot of space between them there. Let's zoom in a little bit. You can kind of see, okay, yeah, they're getting bigger and bigger and bigger, kind of in parallel. So we can see that if you were to start at time equal to 0, right, we do get initial conditions of 2 and 4. And then at least for these initial conditions, your values just grow and grow and grow and grow and grow, right? There's no dip where you get smaller first. Okay, let's go ahead and look at something else really neat. And I think this is linked in Canvas, but if it's not, I will. I would definitely encourage you to play around with this phase plane plotter. This one is not, I know, I like this one pretty well, actually. There are other ones you can look for. So I'm going to write my differential equations. Now be careful here. We do have to use x and y here, not x1 and x2. So if I graph dx dt equal to negative x1 plus 2x2 or negative x plus 2. For this one, for whatever reason, you have to write the star symbol for the asterisk for multiplication. So 2 times y. And then down here, negative 3x1, so negative 3x plus 4 times y for asterisk y. And then you graph the phase plane. What stupid thing did I do? Oh, looks right. What is wrong with you? Oh, I forgot the star times the x. Negative 3 times x. See, it's very particular. Okay, now, oops. Sorry, plus 4 times y. Now let's try that. So this is what the system of linear differential equations, this is what like the whole kind of solution space looks like. And so there's a lot of different curves here that represent the solutions. And let's go ahead and look at, let's see if I can click on it well. So if we start with an initial condition of x1 equal to 2 and x2 equal to 4, which is right about there. Oh, look, yeah. If we continue in that direction, both x and y, or x1 and x2, are just getting larger and larger and larger. But if we had started with different initial conditions, like maybe say, I don't know, x1 equal to 3 and x2 equal to 0, a very different thing would happen, right? You would have x1 getting smaller and y and x2 getting smaller, right? Because we're moving left and down. Now, if you zoom out far enough, maybe, I don't know, let's see what happens if we zoom out. We zoom out. No, it just keeps going that way. So yeah. So depending on what kind of, how do I want to say this? What's the word I'm looking for? What kind of, yeah, what kind of system we have. Oh, I know the word I'm looking for. Sorry. What kind of, there's a word I'm looking for. I can't find it. The origin is an equilibrium point. Let me back that up a little bit. So if you go back to our original system of equations here, sorry, 1 second. So I know it's been a while, but equilibrium, right? So when we talk about equilibrium, it's when nothing's changing. So that means all the derivatives have to equal 0. And the only way that these derivatives both equal 0 is if both x1 and x2 are equal to 0. Because these lines are not the same equation. Right? Think about these as being lines. The only place that these two lines would cross each other is at the origin. So what that means is the origin is our only point of equilibrium. And depending on what kind of solution you have, you might have a stable equilibrium where everything is going in towards it, which is not what we have here. Or in our case, we have what's called an unstable equilibrium because we're moving away from the equilibrium point of 0, 0, right? We're starting here and moving away from it, or we're starting up here and moving away from it, right? We're not moving towards the origin. And then it's kind of hard to see. Well, you can see which way the arrows are pointing, right? If the arrows are clearly pointing away from the origin. And so we'll see in the coming week that there are 6 different types of ways of classifying your equilibrium, whether it's stable, I should say, whether it's stable, unstable, and whether you have sort of things emanating out from it, or if you have like a spiral kind of thing going on. So we'll talk about that more. This is not a spiral, I should point out. Those are the initial conditions we were given. Yeah. So, right, you could have lots of different initial conditions, which will lead to variations. So I will also say that no, I won't say that. I'll stop there because it's 2 o'clock. So that's kind of the whole idea, though, that we're solving the system and then we're classifying what kind of solution we have, whether it's stable or unstable, and whether it's a node or a spiral. Correct. It's not a spiral. Spirals have more turn to them. And I'll just say this right now. Spirals, you only get spirals if your eigenvalues are complex, meaning imaginary. So we'll talk more about that next week. This is an unstable node. So essentially for this one, since both of our eigenvalues are positive, everything is shooting out away from the origin because all of our populations are growing larger and larger and larger. Whereas for a stable node, if both of our eigenvalues were negative, everything would be moving inward towards 0 because as time goes on, negative eigenvalues lead to smaller and smaller values. So yeah. All right.